Alright, welcome back to Word Embeddings, and we will continue with Cbow, or Continuous Bag of Words. And this is basically the problem that we've solved. We have a context word cat, and then we define two embedding matrices, Wi and W0, so that we can predict what the next word is to cat. Now remember, the cat jumped over the fence. We have given cat, and we tried to predict the center word, in this case jump. So this is by predict, and we derive the formula. This formula here, and let's call this y predict. And we have this softmax function. Now let me remind you where this came from. Well, we had our WO transpose, and we had the word at position J. So this is the vocabulary. You have 20,000 words or 7,500. This is the number of words, or the length, the number of rows you're gonna get from this matrix. So basically we're gonna take out one word, and this is gonna be word at index J, and we will call this word VW transpose. Yeah? Now to make things a little easier, because we're gonna sum over J, yeah, and not to confuse everybody, let's just call this word VW transpose, and here in the formula we do exactly the same. So now in the denominator you have this normalization factor to make sure that everything is between 0 and 1. We sum over all words, meaning J is 1 to J is V. So the last word here will be V, and we will start with 1, of VW transpose J times VC. And VC, remember, is the context word. So basically what you have the dot product here of your center word and the context word, which again is a measure for similarity. So we can keep this sum now from J is 1 to V. And what we're now going to do is, well, we're going to compare this Y predict with the true Y. And then of course there will be an error. And what we're going to do with the error is we're going to back propagate the error and update these matrices Wi and W0. And we're going to iterate a few times until Wi and W0 don't change anymore. And this is where we have the optimum. Now how do we do this? Well, we're going to have to define a cost function here. And a cost function, in this case, we will use the maximum likelihood estimate. Yeah? So what are we going to do? We're going to go find a set of parameters, VC and VW, so that the likelihood of observing the center word, in this case, jumped, given the context word cat, is maximized. So the center word here is jumped, yeah, and the context word here is cat. Alright, so that's the formula for likelihood. It's basically this formula, and basically what we have here is the probability of jumped given cat and given Wi and W0. Now that's the true translation of this. Yeah, so we have center word, context word, and we have the parameters theta. And remember that in this case, if we take a window of 5 words, the center word is jumped, and the context word just before jumped is cat. Once we've run through all the motions here, what we're going to do is we're going to move the window of 5 words to the right. Then suddenly over becomes your center word, and jump becomes your context word just before over. And this we're gonna do over the whole vocabulary. And this is how we're gonna build our two matrices. Alright? So, if we assume that all the words are independent, then the likelihood is basically the product of the probabilities, and this is over all words. Yeah, so let's call these Wj. Okay, and J going from 1 to the vocabulary. All right, so this is the objective function. So we want to maximize the likelihood, but the first thing that we're gonna do is, remember, we don't like to work with products. Yeah, we prefer sums. Yeah, so if we take the log, then we have the log of the likelihood, the log of L of theta equals, and then we have the sum over all words, so all Wj's, and of course we have the log of, and then we're gonna replace this with that one, is e to the VW transpose Vc divided by the sum over all words of e to the VWj times Vc. Alright? So simply I took the log here. Now this log here we can write as, it is the log of e to the Vw times Vc transpose minus the log of the sum over all words of e Vwj transpose Vc. Yeah, because the log of a divided by b is the log a minus the log b. Yeah, that's simple algebra. All right. So now we want to maximize that likelihood, or the log likelihood. So when we maximize, we will need to take the derivative and set that to 0. Yeah, and the derivative of so let's call this one small l of theta. The derivative of small l of theta, derivative with respect to Vw, we basically gonna have to take the derivative with respect to both parameters. But let's start with Vw. It is the of L of theta, right? Equals, that's, well, the first thing that I'm gonna do is, you have this sum here, yeah, this product converted to a sum, and just keep in mind very quickly that the derivative with respect to x of x squared plus x to the third equals the derivative of x squared plus the derivative of x to the third. So the derivative of a sum is the sum of the derivatives, right? So I can put this first sum here outside. So let me put this here. That's over all w's. And then I have the derivative with respect to Vw of of this here. So log Vw transpose Vc, yeah, minus the log of the sum of all words, and then we have e to the power of Vwj transpose Vc. and that is just simple algebra. All right. Now we're gonna call this one, we're gonna call number 1, and let's call this one number 2. All right. So now we're gonna look at this one here, and the log of E means that these two cancel out each other. This is the same as VW transpose VC. Okay? Because log and E neutralize each other. And then for the second one, we're looking for, right, this, yeah. And basically what we're gonna do is we're gonna call this F, and we're gonna call this G, yeah. And here we have, of course, that F is a function of G of VW, and this calls for the chain rule. Okay.